Oh, Magic D20, what to learn today? Oh, 19. I guess today we're going to have to go over closure property, complex conjugates, and other properties. To begin, let us go over closure property. Basically, how closure property works is you have to go in a certain set of numbers, so like the natural set of numbers, the set of whole numbers, what we went over in the first video. So to determine if a set is closed under a certain operation, you have to take any two numbers of the set, and when that operation is performed on them, the result has to be another number in the set. If this is the case, then the set is closed under that given operation. Now that is kind of confusing in words, but you'll get the picture once I draw a picture. So let's say we're going to be looking at the set of natural numbers. Let's go for addition as the first operation. So let's say, think of two numbers in the set of natural numbers. Let's say 2 and 5, and we're going to be testing addition. So when you add 2 and 5, the result is 7, which, as we know, is another natural number. Try and think of any example of two natural numbers that when you add them together, the result is not a natural number. Good job. There are none, because the set of natural numbers is closed under addition. However, let's say we were to look at something such as subtraction. Let's take the same numbers, 2 and 5, but test them for subtraction. If you were to subtract 2 and 5, the result would be -3, which is not a natural number. That is an integer. So you know that the set of natural numbers is not closed under subtraction. To determine if a set is not closed under a given operation, you just need one counterexample. As a further example, let's say we were looking at the set of integers. Let's say we wanted to know if the set of integers was closed under division. This one is kind of easy. Let's see if you guys can figure out an example. Can you think of anything? Good job, Timmy. I know you got it. Let's say we had 3 divided by 8. This is a fraction, not an integer, and so it's already not closed under division. So it's not really that hard. You just need one counterexample to prove it's not closed. Alright, now let's get into complex conjugates. So complex conjugates are pretty simple. We use complex conjugates to remove the imaginary parts from complex numbers. So what is a complex conjugate? The complex conjugate of a plus bi is simply a minus bi. And we use this in a couple ways. So let's say we're adding a plus bi and a minus bi. So if you add the complex conjugate of a number with a complex number, the resulting expression is simply 2a. Let's say we were multiplying them, a plus bi times a minus bi. The resulting expression would be a squared plus b squared. And we'll go over why a little bit later. So we use this for these two reasons, but we also use it when we divide complex numbers. So let's go over an example. Let's say we had, 4 plus 3i. We want to divide it by -7 minus 2i. So when you divide two complex numbers, the denominator cannot have an imaginary part. So what we're going to do is we're going to multiply both the numerator and denominator by the complex conjugate of the denominator. And we can do that because a over a is equal to 1. And you can multiply anything by 1 and get the same thing. So we'll do 4 plus 3i times -7 plus 2i, because that's the complex conjugate, over -7 minus 2i times -7 plus 2i. Alright, so first let's do the denominator. We know that when you multiply a number by its complex conjugate, the resulting expression is a squared plus b squared. So this would be 49 plus 4 And the numerator, well, we can just go through this. It'd be negative 28 plus 8i minus 21i plus 6i squared. And when you do that, you get negative 34 minus 13i. So now we'll just put it over here. And 49 plus 4 is equal to 53. So your final expression would be negative 34 minus 13i over 53. And we'll go more in depth into the work involved in this example later. Alright, now let's go over why when you multiply a complex number by its complex conjugate, the result is a squared plus b squared. Now, a lot of you can probably figure this out on your own, but it's good to see the problem worked out. So when you multiply this out, you get a squared minus abi plus abi minus b squared I squared. Now when you simplify this, you get a squared minus b squared I squared. And as we learned when we went over the cycles of I squared is equal to negative 1. So this becomes a squared minus negative 1 times b squared. And these cancel out, and you get a squared plus b squared.
Everybody look out! No! The Justins are coming in! Justin! No! Justin, be gone!
I think it's clear. I think...
The Justins are gone!
Anyways, let's go back to math. So, back to dividing complex numbers. Here I already wrote an example, and I'm just going to go more in depth into the work. So let's say we had 2 plus 3i divided by 4 plus 5i. So what we do is we multiply by the complex conjugate of the denominator. We multiply the numerator and the denominator by the complex conjugate of the denominator, because that is how you remove the imaginary part of a complex number. And when we simplify this expression, we cannot have an imaginary number in the denominator, which is why we go through this process in the first place. So here we have the expressions being multiplied by the complex conjugate of the denominator, which would be 4 minus 5i. So when we multiply out the numerator using FOIL or distributive property or however you like to think about it, you get 8 minus 10i plus 12i minus 15i squared. Which, let me get on this side real quick, this simplifies down to 8 plus 2i minus 15i squared. And we know that I squared is equal to negative 1 from our cycles of I, which means that this is equal to 8 plus 2i minus negative 1 times 15. And when we do this, we get 8 plus 2i plus 15, which is equal to 23 plus 2i. Now that's just the numerator. Let's get into the denominator. We already went over when you multiply a number by its complex conjugate, the result is a squared plus b squared, and I already showed you the work. So you get 16 plus 25. So finally, your answer to this would be 23 plus 2i, that's an I, over 16 plus 25, and that simplifies into 41. Alright, let's get back into these very interesting properties that you learned probably when you were like 2 years old, or if you're Joanna, you learned this year. So let's start with the commutative property of addition. Very easy. A plus B is equal to B plus A. Just take a break if it's blowing your mind. Let's go to multiplication. A, B is equal to, that's right, Sammy, B, A. Let's move on to some more challenging stuff. Associative property of addition. A plus B plus C is equal to B plus A plus C. Chill. Multiplication. A times BC is equal to B times AC. You know what?
That was easy.
Now that we're free from Jessen, let's go over the final 3 properties. And now, you might want to, really, I recommend that you take a deep breath before all of these because they're going to be pretty hard. Might need to pause the video. So, there's identity property of addition and multiplication. To start, we'll go with addition. Basically, A plus 0 equals A. Woo, okay, now let's go to multiplication. A times 1 equals A. Woo! Okay, let's get into inverse property. It's pretty simple. It basically says when you multiply a number by its reciprocal, you will get 1. So for example, 6 over 1 times 1 over 6 is equal to 6 over 6, which is equal to 1. Inverse property. Finally, zero property. This one is pretty good. A plus the opposite of A, or just A minus A, is equal to 0. That's for addition. And the zero property, it's called like the additive property for addition. And for multiplication, A times, no, sorry. We're cool here at Winnie High School Study Guide. We're gonna use C, because C is always left out. C times 0 is always equal to 0. Let's give it up for these very challenging properties. It's gonna be very hard. Good job, thank you, Jessen. Ellen, okay. Well, that concludes our episode. As challenging as this episode was, I would recommend that you work really hard to memorize all these properties because they're hard.
That was easy.